Alright, so something I've been thinking about recently is the precise structure of the history of the last 2 centuries in mathematics. And it's very striking that there is a very definite pattern occurring which correlates to geopolitics, particularly European, actually particularly German geopolitics over those 2 centuries. So you have this foundational moment in the early 1800s, and of course, math existed before that, whatever. There's definite history coming in. But early 1800s, you have the Napoleonic Wars, which basically end with the Congress of Vienna. And this is in about a century before World War One. So we're in the early, really kind of things settled down around 1820, but right. And starting in the 1820s, 1830s, we get this flurry of innovation in mathematics. We get things like Galois theory. We get George Peacock introducing symbolic algebra. We get a lot of stuff. And this extends over the next roughly half century to about the 1860s, 70s, 80s. It kind of roughly fades out. And toward the ends of this, we're getting things like helical calculus. But what's starting to happen is codification of what occurred in the previous half century. So you have this sort of early sort of logicist push by individuals like George Peacock, Augustus de Morgan, and Boole, right? So here, I actually want to read this. Peacock's main contribution. So this was in about 1930 that this was published. Peacock's main contribution to mathematical analysis in his attempt to place algebra on a strictly logical basis, right? This is effectively the kernel of logicism. He founded what has been called the British algebra of logic. Okay. His answer to Messier and Friend was that the science of algebra consisted of two parts, arithmetical algebra and symbolic algebra, and that they erred in restricting the science to the arithmetical part. His view of arithmetical algebra is as follows. Basically, I'm not going to read all of this, but down here, let's see. Peacock's okay, yeah, I'm gonna start it here. Peacock's principle may be stated thus: the elementary symbol of arithmetical algebra denotes a digital, that is like a counting number, a natural number, right? So this is sort of like the precursor of the concept of natural numbers, right? An integer number, right? And every combination of elementary symbols must reduce to a digital. Otherwise, it is impossible or foreign to the science. So, if A and B are numbers, so this is like counting numbers, integers. Well, negatives aren't allowed, so it's actually positive integers. So what later becomes called the naturals. And then A plus B is always a number. That's fine. So 7 plus 13, 20. Okay. But A minus B is a number only when B is less than A. So 3 minus 7, not acceptable. Okay. Again, under the same conditions, A times B is always a number. So 7 times 13, that works. But again, A on B is really a number only when B is an exact divisor of A. So 7 on 13 is not it's not a digital, right? Hence the following dilemma. Either A on B must be held to be an impossible expression in general, or else the meaning of the fundamental symbol of algebra must be extended so as to include rational fractions. So note, this was codified about 50 years later, 50, 60 years later, by individuals like Richard Dadick and Giuseppe Peano. Those people, the logicists. The operations of algebra cannot be defined on the supposition that the elementary symbol is an integer number. Peacock attempts to get out of the difficulty by supposing that a symbol which is used as a multiplier is always an integer number, but that a symbol in the place of the multiplicand may be a fraction. For instance, a times b, a can denote only an integer, but b may denote a rational fraction. Now, there is no more fundamental principle in arithmetical algebra than a times b equals b times a, but this would be illegitimate on Peacock's principle. Right? So you're fundamentally changing how things are working. It brings along with it a degree of clarity, but it also brings along with it some of these contradictions. Okay, so this period between the end of the Napoleonic Wars and roughly the unification of Germany and the establishment of the Kingdom of Italy, you might notice a lot of these important figures from the late 1800s are Italian and German. This is not a coincidence. That period we get a flurry of innovation, but then with the establishment of Germany and Italy, so this is in 1871, right? 1860s to early 1870s, when this unification occurred. You might notice this is roughly the end of innovation. That flurry of innovation, that half century, more or less, of innovation which occurred in the early 1800s. And what we get from that point on is a push towards codification by logicists like Giuseppe Peano, Georg Cantor, David Hilbert, Richard Dedekind, right? And most of these individuals are German and Italian. Okay. Now, so we get this period of codification, and it's actually interesting if you look at individuals like Srinivasa Ramanujan. He basically educated himself with books that came out right about this time. So he ends up being one of the last mathematicians that of any influence who was actually carrying on this innovative tradition. And it continued a little bit further in the physics community, right? So you can see like Minkowski and a few other individuals, particularly in physics, they're inventing fundamental mathematics, but only up until about 1805. And Ramanujan comes in about 1813, and he's still doing it, right? So you have this derivative community, the physicists, who basically they continued slightly longer than the mathematicians in the innovation period, but they still stopped more or less before World War I, well before World War I. But Ramanujan, because this is all he ever saw, he's continuing this tradition up until 1820, his death. I think it was 1820. So you get this interesting sort of anachronism with Ramanujan. And I think that's one of the most interesting things about him, is that because of his limited experience, his limited education, he wasn't actually part of what was then current mathematics. He was part of the previous generation of mathematics. And you can see that very clearly when you look at what Ramanujan is doing. It's much more innovative. It's much more akin to that about 1825, somewhere in there, to 1875-ish period, give or take a few years. I think helical calculus comes out in 1876. But yeah, that kind of period, right? You get, and in that period you get things like Fourier series, right? Very basic, fundamental stuff to what we consider today. And then in this period basically ends with So it starts roughly around the unification of Germany and the establishment of the Kingdom of Italy, and it ends in the interwar period, right? So with like the Vienna Circle and Nicolas Bourbaki. Okay, so what's happening here is this is mostly interwar, right after World War One, right? So we're in the 20s and 30s, and again, dominantly German. Nicolas Bourbaki is French. Okay, what they're doing is they're trying to. They've recognized that they've lost a lot of comrades, right? They've lost a lot of mathematicians to the war, to and to the pandemic of influenza. They've lost a lot of people, and they kind of need to regroup and bring things together and reestablish what they're gonna do. Right? They need to kind of get a new plan going, and they're carrying on this idea of logical empiricism. Right? They've sort of taken logicism and they're just making it more and more and more extreme as we move forward. Like, we're just working on this, and a lot of these names are going to be familiar. You have Ernst Mach, David Hilbert, Gottlob Frege, Bertrand Russell, Ludwig Wittgenstein, Albert Einstein. Right? You have these are a lot of the same names from that period, but now they're old, right? So they're kind of, what they're doing is they're basically passing the torch to the next generation. And Nicolas Bourbaki, these are so a group of students and mathematicians teaching at university in France, who part of what's happening is a recognition that a lot of the people who were really skilled and knowledgeable about the previous century's worth of mathematics were now gone or about to be gone. Like, a lot of them were older or dead. So what we need to do is we need to establish new textbooks which are up to date. Okay? That's the gist of it. So what is happening here is we are, in this period, we are setting the stage for popularization. Right? The goal is disseminate what we have from the previous century. And the reason is tied to geopolitics. It's tied to the war that just happened, the Great War. It's tied to this, just the human condition at this point. Okay? And this founding of this popularization movement continues till about the time, you might notice this year right here, 1936, and notice they're in Vienna, and Nicolas Bourbaki, we're in the mid-30s when we're establishing this. Something is about to happen here, right? Notice Felix Hausdorff, when does he die? 1942. And why? Because of the Third Reich, right? So this individual, Felix Hausdorff, he's considered one of the founders of modern topology, contributes significantly to set theory, descriptive set theory, measure theory, and functional analysis. And he was Jewish, so life for him became difficult after Kristallnacht in 1938, and the next year he tried to emigrate to the US, but he couldn't make arrangements for a research fellowship, so he remained behind. He died in Bonn, I believe. Yeah. In late January of 42, along with his wife and sister-in-law, and they committed suicide by taking a sleeping drug, a Veronal. And they understood what was going to happen, what the Germans were going to do to them. So there is very much, and I mean, so there is a little bit of a bright side to this, right? He's 73, so he lived his life, or he lived a long life, and he did contribute effectively. But what this highlights is there was a mass extinction event which occurred here in these fields, in mathematics, in the sciences, in every industry, honestly. Just because the people that were taken, the people that were lost, there was no filter. It's just kind of anyone can go, right? So you lose these people. And this, when the Vienna Circle was broken up, what happens is the surviving members of it, they disseminate across the globe. A lot of them to U.S., a lot of them to other places around the world, some of them to Russia. They go all over the place. And what they do is they seed all of these places with both this fear of losing their tradition, of losing their traditional knowledge, of losing the knowledge of the previous century of mathematics, of science, of whatever. And they have an almost radical religious attachment to the ideas of logicism and logical empiricism, like this foundation. So what they do is they end up proselytizing this core set of beliefs, and it sort of becomes a global religion. That's just the facts of it. That's what's happening. And the goal at this point is popularization. We want to spread this so that it doesn't die, it doesn't fall away, because we have seen our comrades die. We know that a lot of these people who were really important, really brilliant individuals, they're lost for completely stupid, arbitrary reasons, right? There's no good reason for this, right? So the next, and we're still in this era, okay? We haven't really gotten out of this. We haven't recovered from this. Not that we necessarily should, but this is just part of it. This is part of the history of mathematics right here. And you can see that the political upheavals in Europe are driving the pattern. So when I'm saying things like this is a religion, it's based on actual just observation of what's occurring here, right? It's not derogatory. It's simply true. And there's reasons that it's this way, right? You literally have martyrs for modern mathematics, like this man, Felix Hausdorff. And that is absolutely tragic. It shouldn't be that way, ideally. But that is the situation, right? And you can very clearly see when you look at the past 2 centuries of mathematics, you can very clearly see this 50-year roughly period between the Congress of Vienna and the unification of Germany, and the 50-year roughly period between the unification of Germany and World War I, and then the interwar period. You get this start of recognition that, okay, we need to popularize this, we need to spread this, what we have, so that we don't lose it. And then that just goes into full swing post-war, and we haven't recovered from that. That is the period we are still in right now. So in a lot of ways, the period we're in right now is kind of a dark age for mathematics and sciences, because here you see a fundamental shift in philosophy, right? We're tinkering with the very fabric of what mathematics is. There's conclusions in this that I disagree with personally, but you can see that this is a bold move. by De Morgan, Boole, Peacock, these individuals. This is a bold move in a new direction. We haven't seen that since. That hasn't happened since then. What we have after that, after the unification of Germany, we get codification of that. And then we get popularization of it. And we're still just in the popularization phase. Which means it's stagnant. Things have stagnated. And we just take what was established previously as truth. The problem is the shifts in from one period to the next never occurred because of the quality of the arguments. It didn't occur because of the quality of the ideas. We didn't go from innovation to codification because the innovation was done. We didn't go from codification to popularization because codification was done. We went to them because the human condition required us to. And I think this is a very fundamental part of the history of mathematics that is not recognized. But it's inescapably true. And it also applies to other sciences, physics, astronomy, all of these, all sorts of things, because these things impacted everyone.